Hello and welcome to today's webinar entitled Winning with Java at Market Open. My name's Howard Green. You can send me email at hgreen@azul.com if you're having any issues. I'm hosting the event. I'll be breaking in at the end to share your questions. Just a quick advisory, this webinar is being recorded and we hope to have it live on the Azul site later today. And now I'd like to introduce Gil Tene, Azul Systems co-founder and CTO, and Gil will be taking things from here.
Hi, everyone. I'm Gil Tene. I'm the CTO and co-founder of Azul Systems, and we're going to be talking about a specific issue with Java that we've been asked by many people to address, and how we ended up addressing it in our product and how our customers use it to really get around a common issue with marketed open trading and Java. So the key and starting point to all this starts from a request that we got from a lot of our customers and a lot of our prospects, where initially we thought this might be a rare thing, and it ended up being the most commonly requested feature, or the most commonly asked for problem solution that we've had so far in financial services areas. And the key question there is when the market opens, which is usually when volatility is highest, when opportunity is highest, and when risk is very high, are you fast? Is your normal execution speed up to what you need to do at the market open? And unfortunately with Java, we see this situation very commonly. Java runs pretty fast. People put a lot of effort into getting good fast code in Java systems. They gain all the benefits from building on top of Java platforms for productivity, for speed, for leverage. But at market open, there is a common phenomenon for Java systems where they slow down for a few seconds or maybe even a couple of minutes at the beginning of the market, where during that time, the execution is slower than normal, slower than it is the rest of the day. And when we look at, what is behind that, it really has to do with Java's adaptive qualities, with the things that actually makes Java fast and very fast once it's warmed up. And they really look like this. At the start, Java runs code that hasn't yet learned what fast execution needs to be and what speed and optimization can be applied. So it starts slow and it learns how to speed up. Code that is exercised, code that is run a lot, has just-in-time optimizations applied to it. And as you keep loading code and initializing it at the very beginning of execution, the code speeds up. Now, that aggressive optimization, the aggressive optimization that JIT compilers can apply, applies after a few thousand or tens of thousands of operations have gone through, and the code has actually learned about the behavior and optimizes for it. Unfortunately, when we look at market open conditions where people are preparing for the open of the market, what often happens is that we see a temporary reversion to slow execution right at the beginning, and then a readaptation where speed goes on and on again, and we get good fast speed if we look at the averages, if we look at the entire day. But those first few seconds of transition are often critical. Now, at the beginning, we have what people usually refer to as warm-up. The code learns. We warm it up with things that look like the real execution, hopefully. The code adapts to it, speeds up. But then this other thing, the reversion, is due to a phenomenon we call de-optimization. And I'll get into why the optimization happens very quickly here. When we look at how JIT compilers do what they do, where we get that very good optimization, very good speed, it comes from being able to look at the execution of code and apply speculative techniques to making things fast even when you can't necessarily prove that they're going to be fast. I'm going to use a couple of examples. This is not going to be a deep dive into code, but there are a couple of simple examples that show the logic of that. For example, if we look at this logic where there's some piece of code that sometimes will do one thing, sometimes will do another thing, and then take whatever number we have and do some complex math like extract the logarithm of it before it goes on. if our code profiling that happens during warm-up determines that this red part is always what happens, where all values encountered so far were below 10, the optimizer can actually dramatically reduce the complexity of the code and say, hey, if we ever see a value larger than what we think it should be, we'll just do something really slow and maybe take away the optimization, but otherwise I can pre-compute the result. And a result of that is much, much faster code in that common case, or more importantly, much, much faster code if the assumption that was built during compilation initially is always held. Another example of that would be null checking. Java is a very safe execution environment, and every access to every field is actually protected against accessing null pointers. This is one of the things that makes Java very productive, because you don't get core dumps in Java. You get handleable executions and exceptions, and there's a lot of benefits to that. But that does mean that every access to every field, every object, always has to be sanity checks against nulls. And that is overhead. However, a compiler can safely assume that things are not null, optimize for the case where they're not null, if it can handle the fact that a null could occur and revert the code in execution to a slow case. This is a very worthwhile optimization, a very powerful optimization, as long as taking exceptions and null pointers is a rare thing. And taking exceptions and null pointers is almost always a rare thing, because it would be kind of silly code that would access null pointers a lot. Again, a very powerful optimization that relies on the behavior staying the same way as what we speculated to be and what we profiled it to be initially. So this is only true if you don't encounter nulls, but in paths where you do encounter them, this is wrong and would be much, much slower. De-optimization is the term we use to describe what happens when optimized code has encountered a reason to throw away the optimization and change the way it runs. The optimization is the reaction to adaptive compilation. In fact, it's the thing that enables speculative compilation. So JIT compilers adapt, they speculate, they leverage observations of behavior like the examples I just gave, and they can hope for certain things to stay the same forever as long as they're able to recover from that hope being wrong. And the optimization is the way we recover. Warming up code is a black art mostly because if you just ran the code long enough to compile it, you don't necessarily have stabilized the assumptions in the code. The optimization can always occur in the future if one of the future branches or executions of your code breaks an assumption that the compiler made to make some code ultra fast. And this often occurs well after you think the code is warmed up. So I'll give a few examples high level to potential causes of the optimization. But the first and probably the most important thing to note is let's look at a real-world example, and we see this happen a lot. Trading systems want the first trades to be fast. And as a result, we often see people put a lot of effort into warming up a trading system before they actually run real trades through it before the market really opens. A common technique would be to run enough fake traffic through the system in order to make the code warm up, achieve good optimization, and then once you've achieved good optimization, actually run the real trades on it when the market opens. This is what we hope for, but this is what really happens often. The code is almost invariably going to do something slightly different if it encounters fake messages or not. For example, you may run through your entire logic, but then at the very end say, this is a fake trade. I'm not actually going to send it to the market. So that last part of sending it to the market will not happen. If the compiler sees that and only that is what is executed at the beginning, you have 20,000 fake messages goes through, the optimizer will basically optimize for running fake code and fake messages. And then when the first actual message, when the first actual trade comes through, that trade will break an assumption that the compiler made, assuming that it'll never happen, and the compiler will then revert the code safely to run in a slower, unoptimized mode while it figures out how to really optimize it for the real world. This is a common example we run into in actual trading. And when you look at examples of why this might happen, at the high level, it's almost always because some newly encountered code is breaking an assumption. It may be because this is the first place we've ever called some code that isn't even initialized, or maybe it's the first time we've called a method that hasn't even been loaded. These are common when you look at code that handles rare protocols or rare messages, something that you just haven't built a complete coverage for in the warm-up. We also see often optimizations that happen because dynamic branching or some other unexpected path is taken. And implicit null check hitting a null in the example I gave of a very powerful optimization is another cause of the optimization. There are many others. These are just examples. So this is what we have. We have Java warming up, getting to be fast, but then when it hits the initial beginning of the market, running into some things that break the assumptions of the warm-up, so it goes slow again, and then it learns reality and actually tends to go and stay fast for the rest of the day. What we have is this, but what we want is no slow trades. This is where Zing and ReadyNow come in, and really ReadyNow is aimed specifically at this problem, specifically at the issue of both slowdown at the beginning of the market and the weakness and the danger of having to warm up systems with potentially risky consequences. So what can we do about it? What do we do about it? Well, in Azul Zing JVM, we have a feature set called ReadyNow, and ReadyNow gives us two key things. The first is it avoids the optimizations while keeping code fast. The second, and a very powerful one, is that it allows code to reach optimized levels without requiring heavy exercise, without needing to run through tens of thousands of real-world operations before it reaches the speed that you actually want it to do. And one of the strong and powerful things that we have that allows that to happen is that we can have a Zing run learn from and retain optimizations from a prior run. You can have your yesterday's run and yesterday's optimization decisions affect today's optimization, so you can run fast from the start. We also include a lot of fine-grained control options, things like per method compiler directives, and a lot of flow things that help gain confidence in the speed that you'll have at market open rather than wait to see what happens. Zooming into the logging and replaying of optimizations, in Zing, we are able to, as a JVM runs, record all ongoing optimization decisions and all the statistics that led to them. We don't record the actual optimizations in the actual code. We record the learning and the reasons that those optimizations and compilation happen in certain ways. We also record the dependencies of optimization. So if some code can only be optimized or loaded or compiled when some other code is ready to run, and when certain things have to happen in order, we record those relationships. And this establishes basically a stable optimization state at the end of the previous run, or as far as the previous run had run. When you start a Zing JVM, you can have it use a prior JVM's log at startup to prime the JVM with the knowledge of those prior stable optimizations without this new JVM having to learn them from scratch and having to be warmed up the same way. And those optimizations are applied not immediately at the startup point, but as their dependencies are resolved and as they can be safely semantically applied to the code that runs. ReadyNow has a workflow that promotes confidence in the optimizations being applied, because as optimizations are applied, we are hoping that we exhaust all the optimizations that a prior JVM has had. But there's always that nagging question of, how do I know that my first trade is actually going to be fast? How do I know that the optimizations really have been applied? Am I missing something? So with ReadyNow, you can actually tell whether or not all your prior optimizations have been applied, and if some of them have not yet been applied, you can know why. And that means that from a workflow perspective, you're able to know that there's some 7 things that used to be or had prior been optimized in the long run, but haven't yet been optimized before the market opened. And we can tell you what is missing, what operations those things are still waiting for. That information comes from the dependency tracking that we log. So looking back in pictures rather than bullets in code. We're looking at Java at load start that looks like this. This is the unfortunate market open condition for many trading systems, algo systems, even exchanges and venues. De-optimization is the key cause of the slowdown spike after warm-up. And with Zing, with ReadyNow, we avoid those de-optimizations, flattening out the speed at market open. Now, the other part of this curve that's interesting is the warm-up part. Getting to the speed to begin with is often risky business. So yes, you can get there with some artificial code and artificial warm-ups that you hope is covering things. But we have multiple customers who used to actually warm up by executing real trades, by either executing small trades or executing trades and canceling them. And that is very risky. That can come back and bite you in the real world in big ways, because you are doing business operations simply to get fast, and there's high risk with that. With ReadyNow, that warm-up period can be eliminated because ReadyNow starts fast from the start. We use the prior optimization logs to start up and have the code run fast from the first actual transactions that we'll execute. So you get this flat execution, and you get to run at the same speed all the time. There's one other very important quality here. With ReadyNow, you know with confidence that all optimizations have been applied and that your warm-up or startup or whatever it is that you would have done before is unneeded, or you've initialized everything needed. So you can know ahead of time that your code is ready for the critical operations at market open, rather than hope that it is and deal with the realities if it isn't. So this is Zing and ReadyNow. That's what the feature set is about. And a quick one-liner takeaway about this, and about Zing in general, because ReadyNow is not the only thing we do, is Zing is really the cure for the Java hiccups, for inconsistencies of execution, whether there's stalls in the middle of the day, or slowdowns at market open, or any kind of inconsistent blip where the computer goes out to lunch in the middle of important operations. Zing has been designed for that. It's being driven for that by multiple markets, both financial services and others. And we are basically aiming it at consistent speed and consistent execution. So with that, we've covered the subject matter. And I think we're going to try to see if we can take any questions from the audience.
Sure, Gil, I'm assuming you can hear me. So I've got a couple of questions right off the bat and more to follow. First question is, how long has ReadyNow been available? So
ReadyNow as a feature set was launched roughly a year ago, but it has evolved as a feature set. The first set of things we gave with ReadyNow were the ability to do fine-grained control of optimizations, eliminate some reasons for the optimizations even without pre-recording and replays of logs. And then over time, we've added more and more features. The ability to record full optimization logs and replay them and execute them has been available since late last summer.
That's great. Another question, are there scenarios outside market open where ReadyNow could be useful?
So that's a very good question. ReadyNow is certainly driven by input from financial services firms and specifically by market open and warm-up concerns. So that's why we built it, but we think it has applicability well outside of that specific area. In this talk, I focused on the driving and motivating reason there, and we are focused on market open as a subject here. But if you look at where ReadyNow applies beyond that, ReadyNow basically allows a JVM to learn from a prior JVM or another JVM's optimizations decisions. So we are looking at places where people want to apply ReadyNow to things like continuous delivery, continuous deployment, where code is deployed and redeployed multiple times a week, often multiple times a day. And often those situations involve rolling updates or rolling restarts of runtime components. When you do that in say in a web server commercial environment, The things that you encounter may not be as critical and as costly as the operations market open, but they're still annoying. Every one of the servers that you're rolling will start slow, will encounter tens of thousands of slow interactions before it learns how to be fast. And yes, as a percentage of the overall operations on the day, that's not a huge thing, but you experience this annoying slowdown. Hundreds of thousands of operations on a cluster will go slow until later things go fast. And there is a better way. You can actually use ReadyNow to choose a leader. Say if you have a 10 or 100 server cluster that you're rolling a new version of code onto, you can have the first one produce the optimization log. And yes, that one will have to go through the warm-up and learning exercise on your brand new code. But as it learns, the other 99 servers can then use that optimization log to hit the ground running, so that you have only 1/100th of the slow operations that you would have if you did that rollout without ReadyNow powering it. Similarly, elastic growing and shrinking of clusters of servers has a similar motivation, not just continuous deployment, just starting up more servers and shutting them down. Shutting the servers down is easy. That doesn't slow the servers down. But if you're going to shut them down temporarily and later grow them again, you will have the same slowdown artifacts of learning again when you start. This is another example where applying ReadyNow optimizations that were captured from any of the servers to servers that are growing elastically allows those elastic growth servers to hit the ground running, be fast from the start, and avoid a lot of the slowdown during startup that you see with Java.
Thanks. I've got another question here. How does ReadyNow compare to ahead-of-time compilation?
ReadyNow, interestingly, ReadyNow is a technique we apply in JIT-compiled JVMs, and we believe that JIT-compiled JVMs are significantly superior to ahead-of-time compilation. I gave a couple of examples of the power of speculative optimizations before. The example of profiling, seeing that so far we've only seen values in a certain range and getting much faster code as long as that's true, or eliminating null checks. Those kind of profiling-based optimizations are only safe if at runtime, if they are wrong, the code can be taken away and then recompiled and reoptimized in a different way. That is just-in-time compilation. Without that ability, you cannot do that optimization because it isn't safe. It's not provable. As a result, JIT compilers can do much more aggressive things and end up with much faster code than ahead-of-time compilers can. The cost of that, without ReadyNow, is that you need to accept the fact that you might slow down temporarily if you are wrong. And ReadyNow dramatically reduces the likelihood or the cases where that happens and gives you the confidence, if you run with the right workflow, to know that they won't happen to you at market open, but you will still have JIT-optimized, speculatively compiled fast codes to execute your trades with.
Great. We have one more question from end user. Says, our first user, in quotes, sometimes feels pain from very slow execution. Does ReadyNow help fix that?
Yes, with a caveat. So the very, very first user is going to feel the pain. But that doesn't have to be the first user every day or the first user of every server. Once we collect an optimization log from a JVM that is exercised enough with enough users sacrificing their speed at the beginning, that optimization log can be applied to all future runs of that code. Other servers in the same cluster, new servers that are started up later, or just day to day, whenever you operationally have some reason to restart servers, taking that on as well. That brings me, by the way, to another favorite point of mine, and that is these slowdowns generally occur either at code redeploys or at JVM restarts. And JVM restarts are an unfortunate reality in our industry, where people tend to restart their Java infrastructure regularly, either nightly or weekly, simply because they know that's going to be better. The main reason for that tends to be garbage collection issues. Most of the reasons people will hit a restart button in a Java system have to do with the fact that they get to reset the clock on garbage collection, and the problems that they might have been able to push out for a day or two or maybe even a week will not occur at all if they restart the clock every day or week. But that forces them into a restart into the slow operations for the first users and such every day. And the restart itself, when it's caused by garbage collection, is another thing that Zing eliminates as a need, because Zing eliminates garbage collection problems. There are no pauses to be afraid of, and as a result, there's no garbage collection-based reason to restart a server. That means that generally people run servers much longer when they run them on our servers, and those optimizations are therefore lasting much longer. They get to learn from a longer run, and there is no restart that throws them away.
Excellent. That comes to the end of our questions. I'd like to remind everybody that the recording will be up live later today, and thank you all for your attention.
Thanks, everybody, and come to our site and take a look at Zing. Thank you.